So now we know how to use the normal model, but let's talk about some of its limitations. When we use the normal model, we're making an assumption that our distribution follows the normal model. So that means we're assuming it's symmetric and unimodal, but not all data sets look like this. One way we can see if this assumption is valid is by looking at these what's called normal probability plots. So a normal probability plot checks to see if your assumption of the normal model is a reasonable assumption. So here we have an example of a normal probability plot. And what the normal probability plot does is it plots those z-scores to each observation of the variable that we're looking at. In this variable, what we're looking at is the fuel efficiency of cars. So we're looking at the miles per gallon of various cars that we've tested, and we've recorded the fuel efficiency for each single car. Remember that I said that each observation has a unique z-score attached to it, and so this here represents one observation with a fuel efficiency about 15 miles per gallon, and then the z-score that's associated with it. So the normal probability plot is just a specialized graph that lets you determine whether or not your data is normally distributed and that the assumption of using the normal model is appropriate. So if the data follow a distribution that is roughly normal, what you see is you'll see a straight line, a straight diagonal line. If the data or observations are not normal, then that line is going to curve or bend and it's not going to look like a straight line. And if that's the case, if you don't have a straight line, then you will not have a normal distribution and the normal model will not be appropriate. So here again is our normal probability plot for the variable of miles per gallon for fuel efficiency of cars. And you can see this looks like a pretty straight line that's diagonal across the graph. Here we have a second variable that we're looking at. So we're looking at the weights of various individuals, and we've plotted every single observation along with its associated z-score. These normal scores are the z-scores. And you can see from this histogram that's turned on its side that the distribution is actually skewed to the right. And this is also represented in the normal probability plot by this bend in the line. So no longer do we have a straight line, and so the normal model is not appropriate for this variable of the weights of individuals. So using the z-tables or the 68, 95, 99.7 rule would be inappropriate for this variable, and in fact would lead to very biased and inconsistent, inappropriate probabilities or percents. So you could use them, but it would be inappropriate and would give you very biased estimates. So in economics, we deal with skewed data a lot. Remember that I told you that things that are in dollars tend to be skewed to the right, and as you can imagine, economics, we study a lot of things that are measured in dollars, like income or the price of goods. And so these are skewed to the right because you can't get anything less than $0. But one of the ways that we deal with skewed data is by re-expressing it. So we can transform the data using a function. Typically we do this using the log function, and this allows us to look at elasticities. If you remember from 105, elasticities are a very important metric that we use in economics. But we use that log to transform the data to make it look symmetric. So once you've transformed the data, here we have the log of annual consumption, and that's much more symmetric. So we can apply the normal model to this transformed data that is symmetric, and then we can get our original observations back by untransforming our data set. So again, transforming the data allows you to make the transformed data symmetric and then apply the normal model to that symmetric data. So why is all of this important? Well, it's important to know when the normal model is appropriate to use. If you're using the normal model when the data is skewed, again, you're going to get biased probabilities and biased percentages in your answers. And that's not going to reflect reality. What we're trying to do is get a good model or a good reflection of reality with these statistics. Moving forward, we're going to assume that the distributions that we're looking at for variables are normal. And we're going to go through a couple of problems to see how the normal model is applied. But remember, the big assumption that we've made here is that the distribution of the variable we're looking at is unimodal and symmetric. If that is violated, we're going to have biased estimates.